Okay, let's see. The exam guide has been posted. I'm going to go over that with you at the end of today. I just want to finish off the remaining topics about loops, verifying loops. Let's do that, and then we'll take a short break. And then after that, we'll talk about the exam, okay? Because your exam will be next Thursday. So example questions, latest, I'll make it available around your study day. If I can make them earlier, maybe late Friday, over the weekend, I'll definitely do that, so you can try it out a little bit earlier. And then I'll schedule maybe one review session at least next week, most likely Tuesday. So you guys can connect to the Zoom, and then we can talk about your questions and go over some practice questions if you want to, right? I'll reach out to you about the time. And then lab number 4, make sure you submit in time and also see the idea. I can also briefly talk about it during the review session as well, the material you gotta look out for. And for the bonus opportunity, we still have a chance. If you guys still want to participate, go ahead. It's until tonight, okay? And then office hour, I still have it today and also Thursday. If you want to speak to me, you're welcome to, right? And you can also speak to Andy about your lab as well. For your programming test number 2, I will definitely try to get it done. I still need to meet with the TA. We also got some makeup tests tomorrow. So we maybe early next week, definitely before your exam day, I'll get it available to you. And then there will be, as usual, maybe some days for you to consider if you want any regrading to be done. So also make the deadline a little bit later than the actual exam day. So you do have some time to talk, think about. Okay, I'll reach out to you, right? All right, any question about the course? All right, let's now do a recap, and then we'll continue, okay? So last time we dived into the so-called Hoare triple, right? I think that's the most important concept that we introduced last time, and we'll revisit today, and also by introducing a little bit more rules today, okay? Right, we'll talk about stronger versus weaker assertions, especially if you got precondition and postcondition. They're both assertions. So what does it really mean when you got stronger versus weaker precondition? And what does it really mean when you got stronger versus weaker postcondition, right? That's the discussion we had last time. You can review them. And also, we talk about 2 examples over here. One of them, the precondition is too weak, meaning that it allows certain input value that's going to lead to postcondition violation. On the other hand, for this precondition over here, it does not allow anything that's going to lead to a postcondition violation. However, it does disallow certain value that's not actually going to lead to any postcondition violation, but we're still disallowing that. Should that be a right design choice or not? That's more like an open-ended question for you guys to think about, right? So that one, there's no right or wrong. It's just about the way it is. And also always remember when we talk about correctness for verification, it's really relative to the specification you have for your algorithm, the precondition and postcondition, right? When you don't really consider termination, you can only say it's partial correctness. As soon as you got partial correctness and you prove about termination, it's called total correctness. And that's something we'll also address today once we get to the loops, about how you can verify the correctness of loops. All right, so these are the 2 examples. And the syntax for Hoare triple is really you got precondition here, postcondition here, and both of them should be surrounded by the curly brackets right here. And then whatever algorithm you have should be inside. So this part here can be arbitrarily complicated. It can be a single variable assignments. It can be conditionals, or it can be sequential composition, which we'll see right away after the recap. And Hoare triple goes like this. And you can see the meaning also here as well. Okay. And the most important thing, which I'll highly recommend you put on your data sheets, is a short formula here, which is this. Okay, let's revisit this again. This one is telling you once you get your algorithm with the specification and implementation, you can turn the algorithm into the Hoare triple, right? Once you got a Hoare triple, your goal is to prove that Hoare triple is actually a theorem or disprove it, either way. What you really want to end up proving is this particular implication, which we'll also do again by some more complicated example. You want to, first of all, calculate the weakest precondition for your implementation upon termination to establish the postcondition. What is the weakest one? And is your current precondition no weaker than the weakest precondition? That's what it is saying. That's exactly what the implication is saying. And you can see here, once we given the implementation and once we given the postcondition, this will be the weakest precondition. And your actual precondition here If it is somehow surrounded by the weakest precondition, you're safe. That's basically the implication will just hold. On the other hand, let's say if this is the weakest precondition, but this is your actual precondition. In that way, you got at least one input value over here that is not going to be guaranteed to lead to post-condition satisfaction because it's outside the weakest precondition. The weakest precondition simply tells you only those values that will satisfy the weakest precondition will guarantee that you have no post-condition violation. Anything outside, no. It's logically sound, all right? That may be something you didn't really quite catch on Monday, but you still have time to really digest, right? Okay. And then we just revisit the two examples before. You can see that's where we got the correct program. You can see the actual precondition over here. Sorry, that's the incorrect program. Beg your pardon. This is the calculated weakest precondition, and that one there is actually surrounded by the actual precondition. That's wrong, right? Because you got at least one value here that might lead to post-condition violation, which we spoke about last time. On the other hand, this one here is correct, right? Because you can see the weakest precondition here covers the actual precondition, right? So just always remember this formula here, okay? Of course, not just to really memorize it or just to put on your data sheet, you got to understand exactly what the meaning is, okay? That's the most important part. Right, and we talk about two rules about the WP calculation. If you're given a variable assignment, you will simply take the post condition there and substitute every free occurrence of the variable being changed by the expression. Right, that's something we did last time. We're going to do more today, just to emphasize the idea. Okay, that's variable assignments, and then we did also the if conditional. You got either branch number 1, or if this is not true, you go to branch number 2. You go either way. But the bottom line is both branches should really establish the post condition no matter which one you go to. So that's why we say either this or this. And both of them must establish the post condition, right? So if you go for branch number 1, then you will need to get a WP for establishing the post condition, but the implementation will be just S1 under branch 1. Or you can go under branch number 2, right? So you can look at the rule, and you can feel free to put it on the data sheets, but of course you got to know how to do the calculation, right? We're going to do more example today. And this is the last thing we do. We kind of did it by following the steps, right? Always remember step number 1. If you're given the problem to actually prove some program being correct, step number 1, always formulate a whole triple first. Step number 2, calculate the WP. Step number 3, try to argue, proof or disprove the original precondition implies the weakest precondition it calculates. We're going to do this exercise one more time, okay, today. And that was the last bit. And we couldn't really continue with this example here because it does contain sequential composition. But we're going to do sequential composition right away. So you can continue with this exercise after today. Okay. Any question? John? The same process, yeah. Yeah. So John's question was, what if the post condition here, I can tell you that doesn't really matter. It might contain implication, it might contain quantification, doesn't really matter. So it's still just R, right? So when you calculate WP, you got S and then R. So this R here can be arbitrarily complicated. You just got to do the substitution accordingly. Yeah. All right. And let's now move on. Okay. So let's talk about the WP rule for sequential composition. Yeah?
So if the post condition has implication, are we required to do something?
You can use whatever rule that as you see fit. But of course, if you justify that on the exam, make sure you put down the rule name so we'll understand which one you're using. Yeah. So whether you use a shunting or other theorems that you learn from 1090 doesn't really matter. As long as you kind of put down explicitly what rule you're using, then that'll be okay. Okay. Okay, let's talk about WP, calculation for sequential composition. So what the rule we're going to see is, if I want to calculate WP, and then now the program itself is one phase followed by the other. So I'll say S1 followed by S2, and then after that, I want to establish the post condition. Okay, so think about this part over here. You can think about it's more like a phase number 1. And this part over here is like a remaining faces. How about that? Okay. Because S2 itself could be a sequential composition itself. It could be maybe S3 followed by S4. It could be, as we'll see, right? You don't necessarily always got only two faces. Think about the first and the remaining. And over here, that will be the post condition. So this part over here is the post condition. And what's the WP rule? And the answer is already on the slides, but I want to show you how this can be thought of from scratch. Okay? So what you can think about is how the pre and post state will look like between these phases. That's how you want to think about it. So let's say we got, over here, we got S1. And then after that, we got S2. Okay, thinking that way. So think about we got the pre-states right here. Pre-states. And after that, we got some intermediate states right before S2, but after S1. Intermediate states. And then upon the completion of everything after S2, let's call it the post states. Right? So these are three states, right? Pretty clear conceptually. And the way to think about it is more like a backwards. Think about the final post states over here should really satisfy R, the ultimate post condition. That's something we want to satisfy. Okay? So let's talk about intermediates first over here. What should be the logically weakest state for us to start here so that we are safe to guarantee we can satisfy the post condition? Itself would be a WP, right? So think about this intermediate state here. So this one here will be just the WP for S2 to establish R. So this will be the weakest precondition for this intermediate state to start so that after S2 we can guarantee to establish R. If you can think about intermediate state first. All right. And then what about this pre-states? Think about this guy over here, just like the post condition for S1. Okay. So now I'm going to make some annotation for you. So think of it. Think of this as the post condition for S1 right here. So this is the final answer we can have, right? So now what about the pre-state over here? So that means the WP for S1 to establish the intermediate states. And that intermediate states can guarantee after S2 we can establish the final outcome. All right? So now what's the final thing? WP for S2 to establish R. Okay, I'll pause for one moment here and then you can think about it. So this is the final answer. Let me recap, first of all. If you're given a sequential composition, phase number one, and also remaining phases, the ultimate goal is to satisfy R upon the termination of everything. So the way to think about it is this. Upon the termination of S1, we want to reach a state that is enough for S2 to continue so that after its termination, we are able to establish R. That's the way to think about it. All right? A little bit trickier, but I think that's as complicated as you will get. Right? Any question about this? Interesting idea. I know it's tricky, but it's an interesting idea. Let's apply this right away. Okay? All right, why don't you read this question first? Okay? We're asking about whether or not this particular Hoare triple is actually a theorem, whether or not it's correct, right? So this could be a typical question might be given on the exam. And let's see exactly how you should solve it. Right? I will show you the whole process. Okay? All right, hopefully you got a chance to read it. Okay. So let's see the big picture. Think about this guy over here is the Q. And this guy over here is a post condition R. And this whole thing over here is the implementation S. Let's just recall the little formula I recommend you kind of put on your data sheet. Let's recall that very quickly. So if you got Q executing S and then R, if that's a whole triple, whether or not it's a theorem depends on, so we say if and only if the original precondition should be no weaker than, right? So that means imply the weakest precondition to for S to establish R, right? So that's something I just recapped earlier today. And what should we do? Okay, so we're gonna calculate WP here as a first step. Calculate it first. And then we're going to actually argue whether or not this implication over here is the case. So step number 1 and step number 2, right? It makes sense, right? We're going to follow this order. And step number 1 is the more complicated in this case, but I'm going to do it carefully, right? All right, let's now do step number 1. So step number 1, we want to calculate the WP for the whole program S, which will be temp X, X, Y, also Y, temp. 3 phases. So not necessarily 2. Okay, I'll help you with that, but just copy that down first, and then we'll do the rest together. X larger than Y. So this part here corresponds to the post condition. And this part over here corresponds to the programming statement, right? I'm just copying that before I do any calculation. And very quick reminder about the rule. We're going to say phase number 1 and also the remaining one, right? So I would say here, this is phase number 1. And this is the remaining phases. All right, like that. Let's now apply the rule. So you're going to say this will be equal to, and you're going to put some justification. This will be the format you'll be expected to follow, right, to make it clear for us to grade. And we're going to apply the WP rule of sequential composition. WP rule of sequential composition. All right. So it's going to be the WP for, and this phase here, after executing it, is going to end up in a state that will be enough for this one to be executed and establish that. So itself is a WP, right? If you look back to the rule, it's exactly what we're doing. So that one there is going to be a WP for this whole thing. X, Y, Y, temp. That one there to establish X larger than Y. Okay, so think about what we're doing here is, this part over here is what the WP is about. But we are not done yet, because you can see that this WP itself also got another semicolon. We're going to break it down by applying the WP rule once more. All right. And for that one there, let's see. Think about this is phase number 1. This is the remaining phase. Okay. Let's now do the rest. Okay, just got to be careful. So you're going to say WP rule of sequential composition. So I'm going to say WP, okay, just copy what I used to get, X, okay. And then I want to make sure this one here, after that, is going to establish something that's enough for this one here to execute and establish that. So that itself is a weakest precondition calculation, right? So what I need to do is I'm going to highlight just this part over here. That one there is the further WP I would need. as a postcondition. Okay. So that one there is going to be the WP of X assigned to Y. And then that one there will be WP of Y assigned to temp. And then establish X larger than Y. And think about this part over here is the green one. So we actually got 1, 2, and 3 WP. We got here, here, and here. So ultimately, what we say is this. In order for this whole thing to really establish R, we want to make sure it is the weakest precondition for this one here to establish what this can establish for the final one to really establish this. It sounds a bit weird, but that's really what we're doing. We're breaking everything down into different phases, right? Each one of them is going to establish its own weakest precondition. Okay. All right, let's now, we are done with the WP rule for sequential composition, and now we know how to do assignments, right? Let's now do them, okay? Let's do one by one, okay, carefully. So the way to do it is, this is the only one we can simplify right now, right away. So we're going to go from inner to outer, okay? So what I will do is, let's now say we want to do, let's say this one here. So we're going to say by the WP rule of assignments. So I'm going to copy everything here. Temp, X, and WP, X, assigned to Y. And what about this part over here? Right? We're going to replace every occurrence of Y by temp. Right? So that one there is going to be X larger than temp. Okay? All right. And I'm running out of space, so let me just do the following. That should be enough. All right, let's now continue. Okay. And now let's now look at the next one. Next one will be this one here. And this will just need another WP rule for assignments, right? That one there will be WP rule of also assignments. And it's going to be WP and temp is assigned to X. And now, what about this part over here? So we're going to replace every occurrence of X by Y. Okay? So it's going to be Y larger than temp. Almost done. All right? And then we're going to say this one here, WP rule of variable assignments. And that one there is the final thing that we can do, just the final one. We're going to replace every occurrence of temp just by X, which will be Y larger than X. And one thing to actually double check for this particular example, can you guys actually see what this one is doing? Swapping X and Y, right? If after the swap, X should be larger than Y, before the swap, of course, Y should be larger than X. Makes sense, right? But this is a nice example there just to show to you can apply the WP rule for sequential composition and also variable assignment, right? But I think the rule application itself is really the learning outcome, right? The actual program is pretty trivial, right? But of course, I might give you a wrong program that does a wrong swap, in which case, of course, your outcome should be, it's not, the WP calculation may not be exactly this, right? But you got to know how to apply the rule. All right, so don't lose the big picture. What we have done is just step number one. Step number two, we are going to compare this WP versus the original precondition. Okay? You might be thinking, oh, because this one here implies true, so it should be correct. No, wrong order. You should be checking whether the original precondition implies the WP. Right? Okay, that's a common mistake I'm telling you, which I saw that when I graded your fellow student exam paper. Don't get the wrong order. You have done so much hard work, right? Don't get the last step wrong. Okay, step number 2. So step number 2, that's why putting this formula down on your data sheet is really valuable. That can kind of prevent some mistake, right? I don't want you guys to lose marks just because of that. Right? So Q is going to be true implies Y larger than X. Is this implication always the case? Not really. Right? If you say the other way, of course it would be, but not this way. If you don't think this is the case, well, or this one here, you can simply simplify identity of implication. It's going to give you just Y larger than X. Is Y larger than X always the case? No, you might be given X and Y. That's going to violate this. So I can say counterexample. So not a theorem. You can give anything where Y is less than or equal to X. For example, you might get X being 3 and Y just being, for example, 2. Right? In that way, this one here is simply just false. Right? So this program here is not correct because the precondition here is weaker than the weakest precondition. Okay. Hopefully it's a little bit better about what the big picture is. Right? All right, any question? Yes?
If you give a question in the exam, how many maximum number of cases will you have?
I'm not exactly sure how many maximum. I would say I wouldn't be so mean to really let you calculate 10. How about that? That'll be too many. I would say if you're able to do this one, if I give you a few more, you should be able to do it. Okay. Yeah, I wouldn't give you 10. That's too many.
Can you quantify a few?
Quantify like how many?
Yeah. What do you mean by a few?
A few like a 3, right? Yeah, something like that. Maybe I would say up to 7 or 8, something like that. Yeah. Well, because you're really pushing me for a number, right? I got to tell you some number, right? I'm not saying I'm going to get to 7 or 8. I might get to 7 or 8, right? Yeah. Don't push me any further, right? You're going to force me to change the exam question. Yeah. Yeah. Yeah, I'll give you something reasonable. How about that? Okay. So guys, the main thing is make sure you learn from this example here and know how to apply that, right? If you really don't feel comfortable, I don't mind if you put the whole thing on the data sheets, if you are willing to sacrifice the space, right? Anyway, I'll leave the choice to you. All right, if this is good, so now we can now talk about loops, how we can verify loops. Okay, and just before that, let's see the loops. So there's some general background about loops, approximation by keep executing the body of the loop. So these are very general information over here. So here, especially you can see the bullet points about one-off error, and if you didn't establish the post condition, if you got some improper handling of the borderline case, like something wrong in the body of the loop. So these are the partial correctness issue because they're nothing to do with termination. So the one is about infinite loop. For example, if you forgot to increment the loop counter, right? That's a typical error that you might have maybe back in 1021. So that's more to do with a total, like a termination issue, right? So that's really the main thing you want to grasp from the slides. All right, let's now talk about the syntax of the loop that we're going to stick to, which would be pretty much like what you did in TLA+. And then I'm going to also talk about loop invariants and variants also at the same page as well. Okay, but you pretty much know about invariant and variant already from lab number 1. Very consistent concept, very consistent. Okay, so let's start with you have some loop over here. So this is the loop. All right, so this will be the implementation using some loop. And then the precondition and also the postcondition. So the precondition over here and the postcondition here. And they are the specification, right? Just quick reminder about the terminology. So these two together is the specification. And then, so there will be some Boolean condition over here. As long as it is true, you're going to keep executing the body of the loop. We know that pretty well. So here you can think about if B is true, that means the loop should really continue. And we'll formulate these conditions in a moment. I just want to give you some very quick summary. And if the B is not true, that means terminates. Terminates. Okay. And then the body of the loop over here can be arbitrarily complicated. The body, okay, so how about this? You might be wondering, do you need to know how to handle nested loop? No, not for this course, okay? So the loop body itself may contain variable assignments, sequential composition, or if conditional. That's it. No nested loop, all right? So no nested loop, okay? So you might get variable assignments. You might get if then else, or you might get sequential composition, right? I'll give you guys some example. You know, when you see the example question, you can also practice that. All right, let's talk about the idea about loop invariance and variance. And I'm pretty sure in 3101 you learned about loop invariance, right? We are trying to see that from a slightly different angle, very simplified pattern, which will be enough for our purpose over here. So let's talk about loop invariance. And also we got loop variance. And one thing which I wouldn't just read off the slides, but you can also take a look. I'll point to you. If you look at the slide number 26, so it summarizes about the difference between loop invariance and variance. That one I can expect you to read. Pretty straightforward. But let's now focus more on the visualization to give you more idea. So the loop invariant here is more like a Boolean expression. On the other hand, the loop variant is a natural number, meaning that it shouldn't go below 0. It will drop down to 0 upon termination. That'll be the principle. Okay, but let's see how to understand it. So you can think about this part over here is the initialization, which corresponds to the initialization over here. So the loop invariance may be false in the beginning, but as soon as after we have executed the initialization for the loop, once we have executed, the loop invariance should stay true throughout the lifetime of the loop. Okay, so this one here is really true. Okay. So what we're saying is, before the initialization is actually done, we don't care if the loop invariant is actually satisfied or not. We don't care. Okay. So this point here tells you your loop invariant is established. Loop invariance established. And then we're saying that at the end of iteration number 1, at the end of iteration number 2, and so on. And let's say we after the final iteration. Okay. So now between the iteration, we are simply just going to execute the body of the loop. So this will be body of the loop. And also here will be body of the loop for the second time, and etc. So this will be the final time where we try to execute the body of the loop. Okay. So in between, we simply say the loop invariant is maintained. From here to here, from here to here, etc. Right? We just simply say it's maintained. Loop invariance maintained. Right? And it is also very important to know that right here, this is when we exit from the loop. So when we exit from the loop, the condition B here should be false, right? Otherwise, we cannot exit from the loop. So this is the exit point, which means B and also loop invariance. beg your pardon, should be not B, because the condition is false. On the other hand, for every one of upon the termination for all the other iteration over here, the loop invariance must be maintained, for sure. But we are not ready to exit just yet, so you'll be B. So you really want to watch out for B versus not B over here. All right? B should really remain true until we exit. But loop invariance should always be satisfied. I. That's the main thing. So somehow this visualization here is going to be formulated into Hoare triple, as we'll see, somehow. Okay, we're going to see exactly how. Guys, any question about loop invariance? Good? Okay, hopefully that's clear. And then what about loop variance? It's an integer number. It's a natural number. Okay, so the idea will be we'll start with certain value after initialization. Okay, and the idea will be each iteration is going to decrease its value until upon the termination of the last iteration it's going to drop to 0. That's our definition. I will see exactly how it can happen using an example. So this is at the end of the last iteration. The last iteration, the variance reaches 0. And it's also consistent with how we understand about system variance in lab number 1. For example, you can see between iteration 1 and also iteration number 2, right? Because we know that between the iteration, we're going to execute the body of the loop, right? Again, the same body of the loop. That one there, if you think about, this is the V0, that's the variance in the beginning of the iteration. And let's say this is the variant at the end of the iteration. In that way, it's dropping, right? So we know that it's always the case that V should be strictly less than V0. That's number 1. And also number 2, the variant V should always be larger than or equal to 0, remain a natural number, right? So these are the two proof of obligation we already know from lab number 1. So it's nothing new, right? It's consistent. All right, any question? Let's now see example, okay? Exactly how we can apply it. You will see very similar pattern as we did for lab number 1. Because there's no like a variance construct in TLA plus. Oh, just before I answer your question. So somehow we have to encode variant in the pre-states and variant in the post-states, just like how we did it for lab number 1. Question?
For the loop variant, does it have to decrease at a constant amount, or
Okay, so the question was whether the variance should be decreasing by the same amount. In theory, it doesn't have to. As long as it's strictly decreasing, that'll be okay. But I think that typically the way we can set up the loop is going to decrease by some constant amount, because usually would you use a loop counter to really measure the variance. But of course, for some particular example, you might have like a different amount of dropping. That's okay. As long as the value is dropping, you'll be fine. Yeah, it's a good question. All right, let's try to understand this loop structure here. Okay, and then I'll also go over. Oh, how about we just go over this diagram very quickly with you? Okay, very quickly. So this diagram here kind of show you what can happen when you try to execute a loop, right? Different violation. You might have precondition violation. You might have loop invariant violation. You might have post-condition violation. You might also have loop variant violation. That's exactly how each one of them can happen. Okay, let's now see the flow. Okay, first of all. Precondition violation is very simple because Q here is the precondition, right? Q here is a precondition. If it happens that it evaluate to false, of course you got precondition violation. That was easy. As soon as you got precondition violation, nothing happened. So you don't even bother to initialize variables, right? All right, and then you may have something like a not I. So the I here is the invariance, loop invariance. If loop invariant evaluate to not, like a false, you get loop invariant violation. Okay? We'll see exactly when to really evaluate it. We'll see that. Okay? And also, this will be post-condition violation, right? It is important for you to see this. So B here is the condition that we specify in the loop. So not B tells me that I'm going to exit from the loop. And then the R over here is the post condition, which is over here. So this one here is a post condition. Okay. So this one is saying if I exit from the loop, but the post condition is not true, then I got post condition violation. Okay. And what about loop variant violation? We evaluate this at the end of each iteration. We want to make sure the loop variance, so this is the error condition, right? Just in case you got confused. So this one here violates our expectation that the V should be a natural number, right? If that happen to be negative, of course, we're going to get loop variant violation, right? There's another way to violate it. If somehow this violates that the variance should be dropping, that V should be strictly less than V0. So if you violate either this or this, you're going to get variant violation. If you don't, you can go ahead to the next iteration. Okay. And this will be the final expected outcome if everything goes right. Right? Again, you can see that here, not B tells me that I exit from the loop. And R over here tells me that my post condition is satisfied. This tells me that I got termination and also I got partial correctness. That's total correctness, basically. Okay. So I'll let you guys to really, okay, I already explained each of the condition here. You can look at the flow chart and try to convince yourself it makes sense, right? Just a very simple flow chart to really show you how the loop is going to go. Okay. And let me go a little bit deeper into the syntax over here. Okay. So this will be the syntax we're going to follow. Okay. You're going to declare like a macro. So invariance is going to take some variables, and also variant will take some variable. We'll see example very soon. So this will be some Boolean condition. This will be some Boolean condition, right? So we got loop variance. So this is loop invariance. And this one here is loop variance. We declare them right up front, so we can use them to evaluate. And then we're going to have two meta variables, like in lab number 1. So these are the meta variables to capture the variant value in the pre and post states. Basically in the beginning of the iteration and at the end of the iteration. That's what I'm saying. All right, you can see we got precondition here, we got postcondition here, in the beginning and at the end. And we got some initialization to maybe initialize the variables, etc. Okay? And in the beginning, we simply assert to see if the loop invariant is established. So think about this line over here. It's about establishment. Okay, sorry. There we go. Okay. This one here is about establishment. Established before entering the loop. And we assert this one more time at the end of the iteration. Just make sure it is preserved. Right? Notice that the invariant got checked twice. The first time is only one off, right before we enter into the loop. Make sure it's established. And this one here is at the end of each iteration. Make sure it's maintained. Right? Just notice the wordings. And then we say before and after the body of the loop, we try to evaluate the variance. Okay, the variance before and also the variance afterwards, right? And we want to make sure from here to here, the variant post should be dropping. Number 1. And number 2, the variant post over here should be a natural number. That's something we want to make sure, right? Just like what you did in lab number 1. So it would be worth your time reviewing this together with how we did for system variant for lab number 1. Okay, consistent encodings. I also put it there as assertion just for your reference over here. Okay. All right, so that's the code structure, like a skeleton we're going to follow. Of course, in the actual question, which I'm also going to give you some example, there might be some code over here. There might be some code here for the body as well, right? For now, just skeleton. We're going to see some concrete example. Okay, question. Good. Okay, pretty good. Let's now do one more example here. I would say we do one example here, and then we'll take a short break, and then two more. Okay, one more example. Let's now try to have some concrete one over here and see how to trace it very quickly. Okay, it's actually very straightforward. But let's see this. So first of all, we got loop invariance right here. You can see that one there just depends on the loop counter I. And we also got loop variant over here that also depends on the loop counter I over here. Okay, so this one here is loop invariance, and this one here is a loop variance. Okay, so loop invariance say that I value should be in between 1 and 6 inclusively. And loop variance is 6 minus I. Okay. And then we say the initial value for I should be 1. So think about this one here is more like an initialization. This one here is a bit like initialization. And also this part here is about meta variable. It's not part of the initialization. So this is not part of sinit. Sinit should only consist of the program variables, not the meta variables. Okay. And then you can see that we check here about loop invariance being established, and also checking the loop invariant being maintained. And also we got our loop invariant pre and loop invariant post. Okay, and the body of the loop is right here. Okay, just make it simple. And the practice question I'm going to give to you guys, you will contain some conditional for you to practice. Okay, but for illustration for now, this will be the body of the loop. Basically, we just want to check to see, keep incrementing I until we got to exit. Just make it simple. Okay. What would be the I value, right? So before any iteration, I is going to be initialized to be 1. Right? And then when I is equal to 1, and we try to check to see whether the invariance is actually satisfied. Is it? Is 1 in between 1 and 6? Indeed, right? So that should be true. And we haven't really entered the loop just yet. Okay, so for now, we're just going to ignore these values. And then we want to see whether or not we're going to enter into the loop. Is 1 less than or equal to 5? Indeed. So this is true. That means we are actually going to enter the loop for the very first time. Okay, the first line I want to explain in a bit more detail so you can see how things get started. Now, question for you. How many iterations do we have in total? How many? Based on the setup over here. How many times are we going to run the loop to execute the body of the loop? How many times exactly? 5? Any other answer? 5? 5 or 6? How about this? These seem to be the popular answers. 5 or 6. Okay, be careful. Okay, it should be 5. So at the end of iteration number 1, also 2 and 3 and then 4 and then 5. Okay, at the end. The I value, let's look at the I value first. At the end of the first iteration, I is going to be incremented from 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6. All right? And then, if you look at the Boolean condition over here, that one there is about I less than or equal to 5. Right? So that means for all these value over here from 2 to 5, they will all be true. And at the end of the 5th iteration, once it becomes 6, it's going to make it false. This guarantees termination. Right? And let's now try to look at it, first of all, invariance. How about that? Invariance. Okay? Invariant here, notice that since we say invariant should be between 1 and 6, and I value is always between 1 and 6, it's always satisfied, which confirms what we believe. Right? Invariant should always be maintained and established. So that means the invariant is always going to be true, which is very important. Invariant should never be violated even just after you exit from the loop. That's the main point. Okay? So there will be one exercise for you, actually at the next page. What if, for example, I modified invariant to be something like a 5, for example, right? You will see some invariant violation. Right? Let's look at the pre and post over here. Let's just do 1. When I is equal to 2, when I is equal to 1, in the beginning of the first iteration, variant pre is going to be just 1. I beg your pardon. It's going to be 6 minus I, right, over here. So it's going to be 6 minus 1, which is 5. And then we're going to execute the body of the loop, which is going to increment from 1 to 2, right? And then, so V post is going to be 6 minus 2, which will be 4. All right, so that's some tracing you have to make sure you can do. All right, so that one is pretty good because now we got from 5 to 4. They're both natural number and we're strictly decreasing it. If you follow the same pattern, 5, 4, 4, 3, 3, 2, 2, 1, and 1, 0. That means at the end of that iteration there, is actually going to be dropping to 0. Okay, at the end. Okay. Yeah, that may be 4, 3, 3, 2, 2, 1, 1, 0. That's correct. Okay.
Does it need to go to 0 or? Does it need to go to 0?
Yeah, for our purpose, it should be 0. I think for the simple loop that we're going to ask you, and also what you're going to practice, we just say always drop to 0. Okay. All right, so there's some simple exercise you can do. And there's one page over here. You can give it a try. What if I modify the looping variant to be this? And what if I modify the variant to be this, for example? And what should there be any violation? Okay, think about it, and I'll give you the solution a little bit later. Some exercise for you to think about. Question? Yeah. Oh, I see what you mean. So we are talking about the first violation. So what you should do is go for the flow chart over there. Go from the beginning and then simulate it to see what's the very first one you're going to run into. Yeah, I'm asking about the first one. As soon as you run into a violation, you don't continue. Yeah, exactly. Okay. Okay, give me 1 minute. I'll summarize in this diagram here, and then we'll take a short break, and then one more thing to say after the break, and then we are done. And then we'll talk about your exam. Okay, so let me do one more thing here, which would only take about 1 or 2 minutes. Now, this is also a nice diagram to kind of show to us about how a loop can be visualized, right, rather than flowchart. So here, this diagram also included some like a reference of a paper, right? You don't need to read it, just for reference. It's actually this. I didn't draw this myself. It's actually from some paper. So what we got is initialization. So this will correspond to the S init. So this means as soon as we have executed initialization step, so this is where the loop invariance is established. And then we try to execute the body of the loop for as many times as necessary. So this will be the body of the loop. And for every subsequent states, we are basically saying the loop invariance is maintained. And of course, we haven't really exited from the loop. So here you talk about exit condition. When we exit, that means not the case B, right? Because B is true, that means we still continue to execute. Li maintain, and also B is the case. But exit condition here is not B. Okay? And then at the end of the very final iteration over here, so this will be the terminated states. And that one there you can see it's the intersection of exit condition and also the loop invariance and also the post condition. So these are the intersection. Okay, let's now formulate them. So that means number one, the loop invariant maintained. Number two, we exit from the loop, it should be not B. And also the post condition should be satisfy R. Okay, it's still consistent with the flow chart. It's just that we try to use a different diagram to say it. All right, any question? John?
For determination, is it that it's not B or is it post?
Yeah, the termination, yeah. So remember for the while loop, we actually say while B, right? So that means exit means not B. So not B should really be true at some point. Otherwise, it never terminates.
How come for our proofs we use like the VP post?
V is more like a variant to measure. So we'll get there once we see the proof obligation. Yeah. All right. Why don't we take a short break and take attendance for the last time?